All right, seventh graders, we are here with our first video lesson where I know you are already thinking in your mind, man, my job is to take the best notes that I can take. So we are going to be talking about number operations today, and the unit goal, the goal for this whole unit is I can read, write, represent, compare, and calculate positive and negative integers. All right, everybody, so out in front of you, what you need is your Pre-Algebra Unit 1 note packet. Yes, there are a lot of notes in there, but it's for the whole unit. If you turn to the first page, you'll see I am an integer master. This right here breaks up all the little pieces that go with that big goal of I can read, write, represent what I just read to you. Today we're going to focus specifically on this first one that says I can identify and use basic rational number operations. With that said, turn to the next page in your note packet. You're going to see the first note sheet that we're going to do in this lesson. It is titled 1.0 Number Operations. So make sure this is out in front of you. So how do we identify and use basic rational number operations? Well, think right now about the four basic operations. Addition, subtraction, multiplication, division, right? Sum, difference, product, quotient. So can you come up with the symbols to represent those operations? Also, do you remember what a rational number is? Rational numbers are different types of numbers. They're the numbers you have spent a majority of your math career focusing on. So let's review that. Rational numbers are our counting numbers or our natural numbers. Our whole numbers, when we add 0 to our natural numbers, we get whole numbers. Integers, whole numbers and their opposites. You ended your 6th grade career working with integers. And our terminating decimals, our repeating decimals, and the fractions that go with them. So your job today, 7th graders, is going to be to complete the chart that's in your notes. Let's look at that chart. All right, in a moment, I'm going to have you pause the video. I'm going to have you fill in as much of this chart as you can on your own, then unpause and let's compare our charts. So your job, 7th graders, is next to the word sum, difference, product, quotient, you need to put the symbol for the basic operation. Where it says other words, you need to give me at least 4 other words for that basic operation. All right, pause the video. All right, let's see how it went. So sum, the symbol that goes with that, that's a plus sign. And then here are some other words that mean the exact same thing as sum. That when you see this symbol, it means sum and these words and more. Difference, that's a subtraction symbol. Here are some other words that mean difference. Product, now product is referring to multiplication, and you can represent multiplication in a handful of ways. You can use the multiplication symbol, the X. You could use the multiplication symbol, the dot. When you have a number directly next to another number, when you have a number directly next to a variable, when you have two variables next to each other. So these three right here are showing invisible multiplication. So multiplication can be visible, like the X and the dot, or it can be invisible. Make sure you have these examples in your notes for the multiplication symbol or the product symbol. Here are some words that mean multiply. Quotient. Quotient is division. Here's the basic division symbol. A fraction is also a division problem, right? I would read it as A divided by B. And a fraction bar can also be diagonal like this. So that is also a division symbol. Make sure you have those in your notes. And then here are some words that mean quotient. Make sure you have those in your notes as well. You may have different words than I do in the different boxes. That's fine, but make sure you have all the ones that I'm showing you and all the symbols that I'm showing you as well. Next, if you need to, pause the video. If you're ready to go on, you are a fast writer. Next is you're gonna have a little video on just what is math language and why is it important. You'll see that on the back side of this note sheet, there are just a few more questions, and you'll fill in those questions from the video.
In the 16th century, the mathematician Robert Ricord wrote a book called The Whetstone of Wit to teach English students algebra. But he was getting tired of writing the words "is equal to" over and over. His solution? He replaced those words with two parallel horizontal line segments because the way he saw it, no two things can be more equal. Could he have used 4 line segments instead of 2? Of course. Could he have used vertical line segments? In fact, some people did. There's no reason why the equal sign had to look the way it does today. At some point, it just caught on, sort of like a meme. More and more mathematicians began to use it, and eventually, it became a standard symbol for equality. Math is full of symbols: lines, dots, arrows, English letters, Greek letters, superscripts, subscripts. It can look like an illegible jumble. It's normal to find this wealth of symbols a little intimidating, and to wonder where they all came from. Sometimes, as Ricord himself noted about his equal sign, there's an apt conformity between the symbol and what it represents. Another example of that is the plus sign for addition, which originated from a condensing of the Latin word et, meaning and. Sometimes, however, the choice of symbol is more arbitrary, such as when a mathematician named Christian Cramp introduced the exclamation mark for factorials just because he needed a shorthand for expressions like this. In fact, all of these symbols were invented or adopted by mathematicians who wanted to avoid repeating themselves, or having to use a lot of words to write out mathematical ideas. Many of the symbols used in mathematics are letters, usually from the Latin alphabet or Greek. Characters are often found representing quantities that are unknown and the relationships between variables. They also stand in for specific numbers that show up frequently, but would be cumbersome or impossible to fully write out in decimal form. Sets of numbers and whole equations can be represented with letters too. Other symbols are used to represent operations. Some of these are especially valuable as shorthand because they condense repeated operations into a single expression. The repeated addition of the same number is abbreviated with a multiplication sign, so it doesn't take up more space than it has to. A number multiplied by itself is indicated with an exponent that tells you how many times to repeat the operation, and a long string of sequential terms added together is collapsed into a capital sigma. These symbols shorten lengthy calculations to smaller terms that are much easier to manipulate. Symbols can also provide succinct instructions about how to perform calculations. Consider the following set of operations on a number. Take some number that you're thinking of, multiply it by 2, subtract 1 from the result, multiply the result of that by itself, divide the result of that by 3, and then add 1 to get the final output. Without our symbols and conventions, we'd be faced with this block of text. With them, we have a compact, elegant expression. Sometimes, as with equals, these symbols communicate meaning through form. Many, however, are arbitrary. Understanding them is a matter of memorizing what they mean and applying them in different contexts until they stick, as with any language. If we were to encounter an alien civilization, they'd probably have a totally different set of symbols. But if they think anything like us, they'd probably have symbols. And their symbols may even correspond directly to ours. They'd have their own multiplication sign, symbol for pi, and, of course, equals.